All right, so we got one more type of hypothesis testing we'll do. It's a small wrinkle. It's really similar to what we've already done. I'll kind of work through some problems if we have time, just more hypothesis testing problems. And then Monday, I'll go over part of practice exam A. I've posted on YouTube 2 videos. They're older videos, but it's me working through the same practice exam problems. So practice exam B, all the problems are already up there on YouTube of me working through them. We'll go through some more of specific problems if people have them Monday. Otherwise, I'll kind of go through the ones that I think are kind of good review on Monday. And the exam will be open Monday and Tuesday. You can take it at any time. Once you start, you'll have 90 minutes to finish it. It's 18 multiple choice questions and a short answer, which has like 5 or 6 parts to it. I'll tell you right now, the short answer is going to be a hypothesis testing problem. So the reason why I do that is because I know that it's the newest thing we went over. We're probably still not super comfortable with it. And so I want to make sure I can give as much partial credit to the hypothesis testing part. And so that short answer, make sure you're showing as much work as you know, even if you're a little lost. Anything can kind of help, let me see that you at least have some idea of at least what it's talking about and give some partial credit. So show as much work as you possibly can there for that short answer. Other than that, the formula sheet is up there on Canvas under the in-class, under the files, and then midterm 2 practice materials. So make sure you've got that formula sheet downloaded. The Z and the T tables will be important. And other than that, it'll be kind of similar to the last one in terms of format and uploading your answer to that short answer portion. So are there any questions for me about the exam before we jump into the very last kind of hypothesis testing stuff today? No questions? Okay. All right. So we kind of left off last class. I showed you a little bit of stuff in Excel with hypothesis testing just to kind of help make a little more sense. If we have time today, maybe I'll show you kind of one more example. But we'll kind of start with, just like with confidence intervals, we started out and I introduced hypothesis testing in these situations where we don't know what the true population mean is. So we get a sample mean, and then we somehow had the population variance before, so we could use the standard normal distribution. Well, what happens when we don't know the population variance or the population standard deviation? Well, just like confidence intervals, we said we're going to have to use a different distribution because depending on the sample size, when I convert these values into what I thought were z-scores, they will now be t-scores because it creates not a standard normal distribution, but a student t distribution. Right? So the steps are going to be the same. We identify the null alternative. We have to figure out what alpha we're testing against. We can use the alpha and the type of test to find a critical value. The only difference is instead of that critical value now represents a t value instead of a z value because it's coming from a different distribution. And our test statistical equation looks a little bit different. We'll call it now, instead of a z statistic, we'll call it a t statistic. And the only difference there from what we were doing before is instead of using the population variance, we're using the sample variance. So actually at this point, I don't know if I have it, so let me just pull it off of Canvas because that'll be easy. And it'll let me kind of show you where it is. So in this practice materials folder, let's open up this formula sheet. I'm going to download it just so I can have it on a separate sheet here. So here are our 3 test statistic equations down here in the bottom right corner of that formula sheet. Notice the only difference between these two is instead of using the population variance, I use the sample variance. So let me zoom in a little bit more there. So instead of the population variance, I use the sample variance. So there's still test statistics. It's just this test statistic represents a t value. This test statistic represents a z value. Other than that, the steps and everything are pretty much identical. Okay? So we've got the same steps. We'll just kind of work through a problem to kind of show this. It's almost identical to what we've been doing. Let me switch this video over so when I switch. So we have that we want to test for whether, or we want to test the hypothesis that the average home value in Muncie is something different than 90,000. So identifying the null and the alternative here should be a little bit easier because we're told what we want to test for is that it's different than. So anytime you see this word different than, you should automatically be thinking about, I have a not equal to sign in the alternate hypothesis, right? Not equal to or different than this value of 90,000. So I assume the opposite is true, which is that that true population mean is in fact equal to 90,000. Right, and just kind of writing some things down here, we had 51 homes. We found a sample mean of 85,000, and our sample variance is what, 100 million? So I'm just writing this down so when we switch off of this slide, we can easily kind of transition. So I'm just writing down everything that I'm given. What's the null and alternate hypothesis? Well, I already identified that, right? So I'm testing, is it different than or not equal to that value? So here I'm going to have a two-tailed test. That's a good thing to remember going into it. From there, I can find critical values and I can find the test statistics. So how will I do that? So it's very similar to what we were doing before. So if we think about critical values, now we're looking at a student t distribution and we're saying for a two-tailed test, what are the critical values, or what are the t values here? And it'll be the same value, but one's positive, one's negative. That give me alpha total in my tails. So alpha over 2, kind of in each tail. Right? Well, I can use the table if I know the area I want in the tail. So let's say we use the first alpha of 0.1. Well then, 0.1 over 2 is 0.05. So I want 0.05 in each tail, and I want to know the t-value that gives that to me. Well, the other thing we need here, well, what student t distribution am I using? That depends on my degrees of freedom. So we said the degrees of freedom was simply n minus 1. So here, 51 minus 1, kind of making it easy. We'll use the degrees of freedom of 50. All right. So with this information, we'll go to our student t table. There we go. The area we want in the tail is alpha over 2, or 0.05, so it's going to be this column, 0.05. I then scroll down until I get to that degrees of freedom of 50. So right here. So 1.676, so 1.676 and negative 1.676 will be my critical values. Okay. Any questions on how I found that before we keep moving? I'm going to do this a little bit differently. So once we have those critical values, you can think about your rejection region as just anything more extreme than that, right? Kind of arrows into the tails there for a two-tailed test. So the next thing I'm going to do is say, well, okay, does my test statistic fall in that range? Right? So I can calculate my test statistic. Now, I'm going to show you this for one alpha value, and then we'll go back and figure out what the other ones were. So my test statistic equation is simply take that mean, subtract the assumed true mean. We're still dividing by the standard deviation of our sample means. It's just that now we know that that's equal to the square root of the sample variance over my sample size. And I wrote this wrong here. This is no longer a z statistic because I'm using my sample variance. This is a t statistic, right, coming from a student t distribution. So we go back and we see, okay, we found 85,000. The assumed true mean from our null hypothesis was 90,000. We then plug in that 100 million variance, and my sample size was 51, right? So I was just using the information I was given here and knowing that the assumed true value is what's in my null hypothesis, plugging that in to get my test statistic here, okay? If I do that, I forget what it is, so I'm going to have to cheat here for a second. I remember what it is. So I already kind of showed this to you. It ends up being negative 3.57. Okay. Now, if I looked at this ahead of time, I found a sample mean. Remember, this denominator represents a standard deviation, so this denominator will always be positive. So if I see something below the assumed true mean, it's going to be a certain number of standard deviations below, so I'll have a negative test statistic. If I had seen something above the assumed true mean, I'd have a positive test statistic. So when I looked at those possible answers, right away I could rule out A. Well, I can just rule out A here. It's the only positive value. Okay? So the other one's going to have to be negative. I probably meant to make this one positive so you could rule both of them out. So from there, it's a matter of kind of getting that entered into our calculator and figuring out that that test statistic is negative 3.57. So I can get this all on the same line here. So what I'm going to do next is take that, chords are messing up here. So 3.57 is my test statistic, negative 3. That's going to be somewhere way over here. So my test statistic is clearly in that rejection region, so I can reject when alpha is 0.1, or I can reject at the 10% level. Okay? Any questions on that before we keep moving? Okay. Now, I looked up one alpha value. The alpha values I wanted were 0.1, 0.05, and 0.01. Well, because it was a two-tailed test, alpha was the total area in the tails. The area I actually wanted, you can kind of think about, the area I actually wanted in the tail was alpha over 2. So the values I want to look up are 0.05, 0.025, and 0.005. Okay? So I could have actually done that all at once pretty quickly. So if I go to the student T table, notice if I'm at degrees of freedom 50, right, the areas I want in the tail are 0.05, 0.025, and 0.05. So I can use these 3 columns. At degrees of freedom of 50, those values would be 1.676, 2.09, and 2.678. So I could have gotten the 3 critical values pretty quickly. Once I have those, if I wanted to, what I could have done is thought about, let me see if I can get these here. So we go 1.676, negative 1.676. What was the next one? 2.009, and then negative 2.678. So 2.009, 2.678. And then I could have thought about, okay, here's my rejection regions for each one of these different alpha values. Remember, this was my alpha of 0.01. Because at every single alpha, I'm going to have a pair of critical values, right? So here's my pair of critical values for the alpha of 0.1, critical values for the alpha of 0.05, critical values for the alpha of 0.01. Now I can plot that test statistic, negative 3.57, which is still way over here. So we can see at this level, it's going to be in my rejection region at all significance levels, right? I can reject the null hypothesis at the 1, 5, and 10% significance levels. Right? So that's kind of how we do the critical value approach. So if I know that a t-value of negative 2.678, remember this corresponded to having 0.01 divided by 2 in the tail. So the area to the left of negative 2.6 is about 0.005. So what will be true about the area to the left of negative 3.57? It's going to be even closer to 0, right? It's going to be a smaller area. So can I actually determine what the p-value is here? Because the p-value would be the probability of seeing this test statistic or anything more extreme. And then I have a two-tailed test, so I'd have to multiply it by 2. So I've essentially got 2 kind of tails here where I know that the area is less than 0.005. So if I had 2 areas that are less than 0.005, I know if I add them together, that would give me my p-value. It has to be less than 0.01. So one of the issues with the student t-distribution is that if I'm trying to find a p-value, I have to I can only put kind of this bounds on it. I know what it's in between, or I know it's less than something. So for this upcoming exam, if I give you an example with a sample variance where you have to use the student t-distribution, I won't require you to find the p-value, Because I know we haven't had enough kind of experience with this. We'll kind of maybe do some stuff with that with hypothesis testing after the exam. But for right now, I won't expect you to find a p-value for situations where you have to use the student t-distribution. However, you can still find the critical values, plot your test statistic, and solve it that way. So I will expect you to know how to find critical values using that student t-distribution and kind of plotting your test statistic against it. Okay. All right. So we found our test statistic. All right. Let's work through a different problem. We kind of plotted it against our critical values. So we got our rejection decision, right? That's the end game. We're kind of done there. We can reject at all levels. Okay. So this one brings up a couple additional points. So let's say we have this, we want to test the hypothesis, and I might have changed this one from the original slides because I'm only ever going to phrase things, and I can't remember if I mentioned this on Wednesday or not. I'm only going to phrase the problems in terms of what you're trying to test for, right? And whatever you're trying to test for, that's your alternative hypothesis. So here I want to test, I just repeated the word that, but you want to test the hypothesis that the birth weight of Indiana babies, all right, who use alcohol while pregnant is less than the national average. So you want to see, is it less than that 3,287? You'll assume the opposite is true, that it's greater than or equal to that amount to get your null. You look at the alternative hypothesis, what sign is there? Less than sign. So we've got a less than, or said differently, a left tail test. Okay. And then I can write everything else down, right? Sample size is 400, sample mean, and sample variance was given to me. So now I've got everything that I was given. I've identified the null alternative hypothesis here, so it's going to be C. Because what I want to test for is that it's less than, so I should have a less than sign in the alternative hypothesis. Okay. Now from here, probably going to have to do things like find critical values. Okay. Well, first of all, if I go back, sorry. If I have a left-tailed test, which of these do I know has to be the correct answer? So if I'm looking at a left-tailed test, all my cutoff values, my critical values, the only evidence that goes against the null is evidence on the left side. Well, just like the standard normal distribution, when I'm thinking about that student t-distribution, it's centered with a mean of 0. Right, my student t-distribution is. So is my standard normal. So for a left-tailed test, if my cutoff values are going to be, right, the only evidence that goes against the null are things that are on the other side of 3,287. So left-tailed test, my critical values would always be negative. Right? Right-tailed test, right, critical values have to be positive. And then the two-tailed test, we said we have pairs, right? We have one either side. So right away, I know this is the right answer, right? That because critical values have to be negative. Now, how would I find those? Well, this one's a little bit tricky, right? So these look similar to standard normal distribution values, but that's because if I think about what's my degrees of freedom here, well, that's just n minus 1. So what, 400 minus 1 or 399? So if I look here, notice once we get past 100, we start making big jumps in this table because otherwise this table would be so, way too long. So the closest degrees of freedom we have is 500. Well, remember, this last row represents, if we had an infinite degrees of freedom, we would have a standard normal distribution. So these are the values you would see from a standard normal distribution. So if we round them to the second decimal, at that closest degrees of freedom to our 399, I mean, these values are only off at the third decimal. If we round them to the second decimal, they'll look just like the standard normal distribution values. So if we want to be a little more precise here, what are the areas that we want in the tail? Well, our typical alphas are 0.1, so 0.1, 0.05, and 0.01. So the area we want in the tail, 0.1, 0.05, 0.01. So we go up here. 0.1, 0.05, and 0.01. So we'll be using these three columns, and those are the areas we want in the tail. We're going to get as close as we can to the degrees of freedom. So 1.283, 1.648, and then 2.334. Which, if we round those to the second decimal, will be kind of the same, will look the same as what we would find from standard normal distribution. Now on the exam, I won't give you an example like this where the degrees of freedom isn't on the chart. Like I was just using this to kind of make a point that we're somewhat limited with that table. I would have given you maybe like 501 so that you had the exact degrees of freedom of 500 that you could find in the table, right? But it's the same process as what we did with the first problem. Once you find that degrees of freedom, we could find those critical values pretty easily. So the other thing that we need to point out here is, okay, well, I actually just said that the critical values were 1.28, 1.65, and 2.33. If I look them up in that student T table, well, that's because the student T table only looks, oh, that's not it, only looks at the right side of the distribution, right? It kind of reminds you up here with that picture. So the left side of the distribution, because this is a symmetric distribution around that mean of 0, if you want that same area in the lower left tail, which is what we wanted for this left tail test, it's going to be all these same values, they'll just be negative, right? So it was kind of like I said, when you're using the standard normal distribution, you could look up alpha to get the value of your critical value for a right tail test, and then just remember, oh, it's a right tail test, critical values have to be positive. So it's those three values, but left tail test, negative. So I'm going to kind of redraw this so that we could see our critical values for this left-tailed test will be negative 1.29, negative 1.65, negative 2.33, and these correspond to the 1, 5, and 10% significant levels. Right? So here's our rejection region. And someone asked me yesterday, well, why am I drawing the arrows? I'm only drawing the arrows to make the visual easy, right? So if we calculate our test statistic here, right, and it's somewhere in our rejection region, when we plot it, it's very easy to see what levels we reject at. You can use the rule, which is if your critical value, the absolute value of your critical value is less than the absolute value of your test statistic, this is when you reject. But the visual of that is, okay, when I'm taking the absolute value, I'm ignoring the negative sign. So if my test statistic is kind of larger in absolute value, I reject, right? It's just easier to see when I draw it out that way. So at this point, it's just a matter of, I could use that formula sheet as a reminder that my test statistic equation is right here, right? So I'll plug in my sample mean, my assumed true mean, my sample variance, and my sample size, right? If I do that, right, just plug those in, I get negative 4.6. Well, now, first of all, if I'm looking at these possible answers, I found the sample mean that I found was below the assumed true mean. So I know that I'm going to have a negative test statistic, right? It's going to be the sample mean I found is a certain number of standard deviations below. So right away, I can rule out A. I know it's B, C, or D. Once I plug those values into my test statistic equation, I end up with negative 4.67, or negative 4.67 if we round to the second decimal. So the next step, now that I have my test statistic, is where does that fall? Well, once again, we have kind of an uninteresting example. I shouldn't say it's uninteresting, but we just have a test statistic that is so extreme that it's clearly in the rejection region at all three levels. Okay? So I can reject, once again, with 1, 5, and 10% significance. Once again, what would the p-value be close to? Well, if the area to the left of negative 2.3 is 0.01, the area to the left of negative 4.6 is going to be really, really small. A p-value approximately 0 there. Right? So we can't actually find it because our table is limited, right? The last area that we actually see in our table is 0.005. So any test statistic that's out even further, the p-value is just going to be smaller than 0.005. Okay? Any questions on that before we keep moving here? All right. So I think I'm just gonna, to kind of help those who kind of learn with seeing the Excel examples, I'll work through an example by hand and kind of simultaneously in Excel. So let's go to that hypothesis testing blank file with unknown population variance, right? So those are the situations that we've been working on. So I'm gonna do, instead of a two-tailed test here, well, we'll do a two-tailed test because I'm gonna change this. I don't think we haven't done a right-tailed test today. So I wanna make sure we see a little bit of everything every day. So let's do a right-tailed test here. To think for the proportion, we ended up changing this the other day to a two-tailed test. So I'm gonna change this one to a right-tailed test for today. So I'm gonna change the hypothesis value to 14, okay? And all I did here was I had some data on the age that one of these individuals first tried an e-cigarette. Some of them got started pretty early, got a 9 in there. So I just found the sample mean, the sample variance, and my sample size, right? Sample size using the count function, sample variance, var.s, and the mean by using that average function. So just a reminder, kind of here's my sample size n. So all I'm gonna do initially is use Excel to be a calculator for me. So I know that I want this test statistical equation because I only have a sample variance, right? So only have a sample variance. So I'm just gonna enter that equation into Excel, right? Kind of let Excel be my calculator. So take the sample mean, and actually, let me see if I have it written down here so you can kind of see it as, here we go. All right, so I'm gonna take my sample mean minus that assumed true mean, which I have over here, divide it by the square root, so SQRT, of my sample variance divided by my sample size, right? I'm just using Excel to be my calculator. I don't have to type these numbers in. I can just click on the cell that they're in. Okay. So this should give me my test statistic. So right away, my test statistic is what? I know the sign of it would be, well, I found a sample mean above the assumed true mean. If the denominator is always positive because it's a standard deviation, the numerator tells me the sign. So if I see a sample mean above the assumed true mean, I've got a positive test statistic. Okay? Sure enough, I get a positive test statistic. Now, what's my null and alternative hypothesis here? Well, if I'm doing a right-tailed test, and this is my value, I don't have kind of a word problem like spelled out here, but right-tailed test, we know that means we have a greater than sign in the alternative, and the value we're testing against is 14, right? So my null would be the opposite, that it's less than or equal to that. Well, I found evidence that goes against the null. Doesn't look like it goes against it very much, but notice we got a pretty big sample size here, right? So that very large sample size, one thing we talked a little bit about last class as well, is let's think about how that sample size is going to impact things, right? If I have a really high sample size, what's that going to do to the standard deviation of my sample means? Right? Well, it drives this fraction down, larger denominator, makes this smaller. Well, now that my denominator for the overall fraction is lower, that actually makes my test statistic larger, right? And if I'm thinking about a larger test statistic, right? Let's do, I'll just redraw it. So if I have a larger test statistic, that's going to do, so think about if we go from a scenario, we're looking at a right-tailed test. If my test statistic is here, so we'll call this kind of like T1. Here would be my p-value, the area to the right. If my test statistic gets larger, call this T2, well, notice my p-value is going to get smaller, right? So a byproduct of increasing my sample size led to a larger test statistic, sorry, this should be a T, which led to a smaller p-value, Well, if I only reject when the p-value is less than alpha, if I have a smaller p-value, I could say that I'm more likely to reject the null. And I'll move this in a second, sorry. Right? So if my p-value goes down, I'm more likely to reject. Okay? So when I have this really high sample size, I have like 6,000, I think, it's probably going to be that it's going to be pretty likely we can reject whatever value we assume the mean is. So kind of keep working on this. So we got our test statistic. So how can I find the p-value? Well, when we were dealing with using the table, we said we were limited in these situations. We can only put a bounds on it. However, in Excel, that's not the case. So when we were doing the proportion one the other day, oh, I've already erased it. Let me see. I think I have a completed. Right? When we were doing the proportion the other day, we used that norm.s.dist. Right? So it's going to be very similar. If we have, oh no, what did I do? Okay, so it's going to be very similar when we have this unknown population variance. It's just now instead of using the norm.s.inv, I have to use t.inv. Okay? Now, remember, we're dealing with a right-tailed test. Okay? So when I use Excel, it's thinking about the area to the left. So when I want, sorry, I'm showing you how to do critical values. We're doing the p-value approach first. T.dist, right? I have my test statistic and I want to know the area to the right. Well, the function in Excel, t.dist, tells me the area to the left. Right? So if I select my test statistic and then comma, well, what's the degrees of freedom? My sample size -1, and then comma 1, making it cumulative. This is going to give me the area to the left. Right? So I hit enter. And this area is approximately 1. So what would the area to the right of it be? Well, 1 minus approximately 1 would be approximately 0. Right? So what I need to do here is to get the area in the right side of the distribution, or to the right of the test statistic for this right-tailed test, 1 minus. So you know that test statistic of 8 is pretty large, right? So the area to the right of it really should be pretty close to 0, which is what we find. Well, what if I want to find critical values? Well, that was where, if I'm thinking about a critical value, it's going to be the cutoff value that gives me alpha in the tail. So, like, what critical value gives me alpha to the right side here? Well, this is where, similar to with the proportion example, we use norm.s.inv. I use t.inv here because I know the area I want in the tail is alpha, right? That probability I want is alpha. Comma, the only other thing now I need is my degrees of freedom, which is the sample size -1. And the only issue here is if I'm looking up 0.01, that's the area in the left tail. With a right-tailed test, the alpha that I wanted was in this upper right tail. Right? So if I'm trying to find the value such that the area above it is 0.01, then the area to the left of it has to be 0.99, or 1 minus that. So I could do 1 minus alpha here, and it'll give me my critical value. Or I could use that t.inv, look up alpha at my degrees of freedom, so n-1, and then just remember, oh yeah, it's going to give me kind of the negative value. I have a right-tailed test. I know that because it's symmetric, it should be that value, but positive. So I can use that absolute value function, just ABS, to get that exact same value. Okay? So now I've got my critical value. I can think about, if I plot that critical value, where's my test statistic? Well, 8.22 is going to be way over here. Right? If I plot 2.3, I can do that real quick. If I think about plotting my critical value here, what is it, 2.33 approximately. My test statistic is 8.2. I'm clearly in that rejection region. I'm going to reject the null. Okay? And similarly, if I look at my p-value, well, the p-value is definitely less than 0.01. So our decision there is if the p-value is less than alpha, we reject. Well, 0 is less than 0.01. So no matter if we use the critical value or the p-value approach, we reject it in both situations. Right. And I could get fancy like I did before and use the if statement to make, put the word reject or fail to reject in here. I won't kind of waste too much time with that since it's not going to be something you need to use for the kind of upcoming exam. So, yeah, so because we have such a high sample size, right, we end up being able to reject a lot of values that we, even if it's really close to what we see as a sample mean. So even like 14.15, okay, we can just barely not reject it here, right? Just right outside of being able to reject for an alpha of 0.01. However, if we change alpha to 0.05, right, well, our p-value is less than alpha. Our test statistic is more extreme than the critical value. So, at the 5% level, we could reject here. Any questions on anything there? Anything in Excel specific to this problem, how we work through it? Notice, it is powerful to use Excel here because we're limited in the table to where it's really hard to find a p-value for these student t examples. But in Excel, we can do it pretty easily, right? Just using that t.dist function. And, for a right-tailed test, we had to 1 minus because we're looking at the area to the right. Any questions on that? Wait for a second. Make sure there's nothing in the chat. All right. So let's go down here. So we kind of have a synopsis of the p-value and critical value approach here. And we'll work through just some more hypothesis testing problems. So I usually have these set up so we can do a bunch of different examples that have slightly different numbers. I'm going to just use kind of this guy right here. So the first set of numbers. So we've got what type of tailed test here? Two-tailed test. If I want to find the test statistic and p-value and the rejection decision, and I have a known population standard deviation of 620, and I want to do this test at the 10% significance level, which would be an alpha of 0.1. So I've got this two-tailed test, and I go out and I get a sample, and I find a sample mean that's above that assumed true value. Right? So what am I doing here? Well, try to kind of draw this, get all our information down, and then we'll switch so we can actually see it. So I know that my sample means should be normally distributed around whatever the true mean is. Well, I've assumed that the mean is, what, 9,200? I then find a sample mean of 9,290. Okay. Now, the p-value would be the probability that I saw something as far away from that assumed true mean as I did, or something even further that went against the null. Well, it was equally as likely I had seen something as far away, but on the opposite side. So what? Over here, I would have a tail that's of equal size, right? So this is my two-tailed test. I can find this area, but then I have to multiply it by 2 to get my total p-value, because it's only half the p-value. So what I'm going to do is I'm going to convert this into a different distribution. It's either going to be a standard normal or a student t. Well, I know the population standard deviation. So if I have a known population standard deviation, I'm working with that standard normal distribution. Anytime I've got proportions or a known population standard deviation or variance, I know that I'm dealing with that standard normal distribution. I can calculate my z statistic or my test statistic here. Right? So how am I going to do that? Well, we could look it up, I guess. I shouldn't have switched off. We could look it up on the formula sheet, which is where I'll show you in just a second. And we see that it's almost identical to what we were just doing. It's just that instead of the sample variance, we use the population variance, right? So this is my standard deviation of my sample means. Now, this problem's a little tricky So the sample mean we found was 9,290. The assumed true mean was 9,200, divided by the square root of. Now we were told the standard deviation, the population standard deviation was 620. If we're only given the standard deviation, this sigma squared is the variance, so we have to kind of just plug sigma in and still square 620. And I forget what the sample size was. I think it was like 105. Let's see. Yeah, 105, right? And our standard deviation for our population was 620. So once we get everything kind of plugged in here, this should give us our test statistic value. Right? Let's see. I don't know this off the top of my head, so let's go. Let Excel do a little math for us, right? We got what? 9,290 minus 9,200 divided by the square root of 620 squared divided by 105. So about 1.49. We'll call that 1.49. Right? So 1.49 is my test statistic. Right? From here, how do I find the p-value? Well, the p-value is typically the area to the right, but for a two-tailed test, it's that area to the right. But it was equally as likely I would have seen something below that assumed true mean that also went against the null. Because the null hypothesis here was just that it's equal to 9,200. So I can find this area, right, using the tables, right? And there's kind of two ways of doing this. For a two-tailed test, I could look up negative 1.49 here and like get that area. I know it's the same, and then multiply it by 2. Or I can look up 1.49, but the table is going to tell me the area to the left. So if I look up 1.49, on my z tables, so I go down here, keep going, 1.49, 0.9319, so 0.9319, I wanted the area to the right, so I subtract it from, 0.9319 was the area to the left. I want the area to the right, so I subtract it from 1, so you get what, 0.0681 here. But it's a two-tailed test, so the last step I have is to multiply that by 2, 0.1362. So I'm doing math in my head correct there. So my p-value, right, is a little bit trickier. I had to kind of find this area above my test statistic, then multiply it by 2 because it's a two-tailed test, and then I get my p-value of 0.1362. Okay. So 0.1362, I could think about, I could be asked a question, what levels do I reject at? Well, once I have my p-value, I only reject if the p-value is less than alpha. Right? So 0.1632, no, I lied. 0.1362 won't really matter because if I compare it to any of my typical alpha values, it's not less than any of them. So I fail to reject at every single level, right? The probability of seeing what I saw, if in fact the true mean was what I assumed it to be, that probability wasn't below these thresholds I set. I still had a 13% chance that I saw the sample mean that I did. Okay. Any questions on that? Okay. So because I wrote the exam, I'm really kind of hammering this today. Oops. I really want to hammer this home today. So let's say instead I have the exact same sample mean, but I find a higher sample size. I wrote the exam, so this is a good one to know. If I take a higher sample size, what's going to happen? Okay. So what are the kind of resulting things after I take a higher sample size? So if n goes up, and really trace this all the way down, it's going to drive up that standard deviation, sorry, not drive up, drive down that standard deviation of my sample means, right? If the denominator gets larger, this whole fraction gets smaller. Because I have a smaller standard deviation, seeing something the same distance away from the assumed true mean is going to be a larger number of standard deviations now. So my test statistic has now, right, increased. Okay. We said if my test statistic increases and is now out here, well, now the p-value, or kind of the area that's more extreme than it, is going to go down. Okay. Because my p-value went down, I'm now going to be more likely to reject, because if my p-value is smaller and I only make rejection decisions based off of when p-value is less than alpha, well, if my p-value is smaller, it's more likely I reject, right? So kind of understanding when we take higher sample sizes, the ultimate effect is that I'm more likely to reject. Okay. So another thing I wanted to kind of point out that I think will be helpful for the exam is we really have three situations, and this is kind of typically after this exam we'll start to get more. So people start to get a little confused at this point. I'm going to try to save a little paper here because I got some classes after this, and I don't know if I can run downstairs. So we've got three scenarios. Right? So the first one is we're looking at a sample mean. We want to do a confidence interval or hypothesis testing. Well, if I'm given either the population variance or the population standard deviation, right, those are known, I can use that standard norm or that Z table. Right? Or if I'm looking at proportions, right, I get to use the Z tables there as well. The only time I need to use the student T up to this right now is if I only have a sample variance or a sample standard deviation, and I'm looking at a sample mean, then I use that student T. So that's kind of one way to kind of keep track of them. So I can think about here, another way of saying this is known population standard deviation, and here kind of we have an unknown population standard deviation. All we have is a sample standard deviation or sample variance. Any questions on that? Okay, just some last kind of minute or last suggestions going into the weekend. I'm sure I'll kind of reiterate this on Monday as you're kind of doing some last minute preparing. So for the upcoming exam next week, the best thing to probably do is look over those two practice exams. The answer keys are pretty, have the formulas and everything that you would need. You've got me working through, at least right now, practice exam B on YouTube. I'll get some other older videos of me working through these of practice exam A. I just have to have the old videos, just got to kind of cut them up and make sure that it's just those specific questions. And then after that, I would look at maybe some of the online quiz questions that can kind of be helpful. Just see how to work through these. I'd look at the procedure of what we did for even the Excel assignment, going back, and really anything that I've drawn in class that you took notes on would be a good thing to look at kind of after that. But those practice exams will be where I spend the majority of my time, okay? It's got everything that you could kind of be asked about, or kind of all the principles kind of all in one place, okay? All right, are there any other questions for me? Otherwise, we'll get out of here and I'll see you guys on Monday. Questions? All right, we'll see you guys on Monday. Have a good weekend.